So in this video, we'd like to look at a new concept, which is called the eigenspace of a matrix M. And it is defined by first finding all the eigenvectors of M first. And you have to look at the span of all these eigenvectors of M. And let's say now M actually has size n by n. And please look at the meaning of this. I mean, if M is actually having size n by n, basically, if you look at this matrix, you actually have n rows and n columns. It means what? It means each eigenvector is actually in the r-dimensional space n, right? Because each eigenvector basically has n spot and n coordinates. We can think of it as inside the vector space Rn. And no matter what number of eigenvectors you have, of course, at most, I'm talking about at most, the span of all the eigenvector actually span the whole space Rn. That's the most. That's the most. It can be less. Sometimes the dimension of this space can be less than n, of course. That's why I'm saying that at most, you can get a basis of this span with n linearly independent eigenvector. That's the most. And now my question is here. Under what conditions for the matrix M will we get the property that we actually have the maximum dimension n for the eigenspace M? And I'll try to skip some mathematical proof, but I'll just give you some hint based on that. So you see the first note is very important. Surprisingly, it's based on the number of different eigenvalues you have. Please recall the fact that for a matrix of size n by n, at most, you can have n different eigenvalues. That's the most. Let's say that's the maximum case. All the n eigenvalues are different. And I'm claiming basically that in that case, M would have n linearly independent eigenvectors. And in that case, of course, we'll get this condition. The span of all these eigenvectors has the n-dimensional space, right? That's the maximum. And it's a very good condition to have, right? And you may be wondering what happens if you don't have the optimal condition that all the eigenvalues are different, or maybe you have less number of eigenvalues. So you see the second point is the more interesting part and is the tricky part. If M actually has less than the optimal number of distinct eigenvalues, then the answer may be yes, maybe no for any linearly independent vectors. There's a second question here. You may be wondering why I'm asking such a strange question. And surprisingly, there's lots of theory behind that, but we'll look at it in the later videos. And for now, let's look at a couple of examples based on what I said here in the two conditions here. So if you look at such a simple matrix 2 by 2, and please recall that at most you get two different eigenvalues and two different eigenvectors. Different means linearly independent for the eigenvectors. And I think this one is fairly easy because to find the eigenvalues, we have to solve a determinant equation. And this matrix is actually quite easy to write down now. It's basically just same as this because it is a upper triangular matrix. Basically, you see for the determinant equation, we basically have this. And basically, it means the lambda actually takes two different values, right? And it gives you a sense that we expect that the eigenspace of M to have dimension 2. Because we have two different values for a 2 by 2 matrix. And of course, you can proceed to find the two linearly independent eigenvectors to span this space. So I just write down the steps here. I trust that you're able to find it yourself because this case is quite easy. So you can look at my computation here. For the first eigenvalue 2, we actually have the first eigenvector 1, 0. For the second eigenvalue, we actually have the second eigenvector. It's quite obvious. These two eigenvectors are linearly independent, right? Basically, they form the standard basis of our two. And these are the two basis vectors we have in this case that generate the eigenspace to have two dimensions, right? Basically, we can say it span the whole space R2 for the eigenspace. And let's look at the second case here. Please look at the current matrix now because it's an upper triangular matrix. And if you solve the determinant equation, we expect that we get the eigenvalues, which is simply from the diagonal entries, which means we have a repeated eigenvalue because two are the same, right? Along the diagonal entries. And now please find all the eigenvectors. Please look at this case. M is actually having size 2 by 2, but you only one eigenvalue. It does not automatically imply that the eigenspace has dimension 1, it doesn't imply that you have to find it out yourself. And in this case, for this eigenvalue, the single one, we actually found only one eigenvector. So we call this eigenvector 1, 0 here. Because we have less than optimal number of eigenvectors. Of course, the eigenspace now has one dimension only, right? Because it is only spanned by only one vector in the basis, and the dimension is 1. So it's less than the optimal number, because the optimal number is actually 2. But as I have emphasized, the fact that it has less than optimal number of eigenvalue does not automatically imply you have only one eigenvector. So let's look at another example. You can look at the current case. It is a diagonal matrix, and once again, we can think of it as a special case of upper triangular matrix. It means this case is quite similar to the last case in the sense that we can read off the eigenvalues from the diagonal entry. Because these two numbers are the same, we actually get only one eigenvalue. And please find the number of eigenvectors now. So you see now the eigenspace actually is two-dimensional because of the fact that if you look at this matrix, it has rank 0. Because both row 1 and row 2 have 0 vectors, right? If you use the rank nullity formula, you can understand that the nullity must be 2, in the sense that you need 2 free parameters to write all the solutions down. It basically means the dimension of the eigenspace is 2 now, because it is actually spanned by 2 linearly independent eigenvectors, and of course it is spanning the whole space R2 in that case. And as you can see, it's quite a tricky problem to determine the number of eigenvectors, especially in the case that you have less than optimal number of eigenvalues.